and also some questions for the following speaker. The Q&A session will be right after the presentation by Rodrigo. And the questions that come through Zoom will be made by me. The questions that are made here on site, we will have wireless mics so that we can facilitate those questions. Okay, my apologies. Let's start with the presentation. What I have come to share with you here today is a process by which we have developed a model to quantify the amount of energy that is generated by the Madrid subway network. It's not a process that was an aim in itself, but it's a concurrent process with other projects that we have undertaken with the idea of calculating some power consumption parameters. And that resulted in this data being available, data that is quite useful to have for a number of reasons. Firstly, I wanted to make a small presentation of what Metro Madrid is as a company. In addition to transporting passengers, many of us at the Metro work hard to try to optimize the processes that make sure that every day we can offer you the necessary level of service, of public service. And also, we have to manage a significant number of tasks relating to maintenance and the operation of the entire network, both of trains as well as the facilities that we own. Some of the main numbers I'm going to share with you. Here you have a picture of the Granbia subway station because it's beautiful. And this is something that was erected because of Mr. Palacios, who made that access, an access that we've tried to replicate. I'm showing it to you to remind you that Metro Madrid is a company with more than 100 years of history. We are the third network in length of subways in Europe, the ninth in the world, 14 lines. And in the year 2019, which was the last year before the pandemic, that has resulted in a significant recession in the number of passengers pretty much worldwide. We were able to transport 183 million people with a significant, 2,400 coaches. And that year, as I said, we transported nearly 700 million people. To do that, Metro de Madrid, which employs 7,000 people who are staff, plus an additional 7,000 people who are contractors, who are one of the main employers of the Madrid.
Poder llevar a cabo este servicio también conlleva un coste importante.
Being able to provide this service has a cost. It was more than 500 gigabytes an hour in 2019, which is the total consumption of middle-sized cities such as Santander in the north of Spain. This was the outcome of a 10-year process where we tried to introduce a lot of energy savings, and we have reduced in a 25% the total consumption for equivalent scenarios. But we're going to talk about generating heat in the underground network. So how much, when, and where is that heat generated? Through what channels? Professor Laloy showed us a magnificent device in order to measure this. When we started with this project, we did not have a device to measure the generated heat, but we can indirectly measure the energy consumed and also the temperature. So we developed a mathematical model that could predict the environmental internal conditions in different scenarios that, to our view, would affect this process. Basically, the movement of trains, the movement of users, the geometry. Those were the main variables, the main parameters that in our view could have an impact in this. And we wanted to compare our results in two stages. First, we would model the energy consumption, and secondly, we would evaluate the heat generation and the temperature in the facilities, and we would compare that with the temperature sensors that we had and with the network analyzers that tell us about the energy consumption. So our goal basically would be to see if our methodology was valid. It is a bit complicated. We know that it's not the brightest one, but we needed to do something about it. So it would give it a realistic approximation to the amount of thermal energy generated that would be available potentially. That was the idea as a potential of the underground network as a renewable energy source. So this was uh, a difficult and challenging process. The main generator of heat in the network is movement, of course, the movement of trains, and also the electrification of the system. As you can see here, this is the cycle that makes electricity being transformed into movement for the trains. And that is a very efficient process, but there are some exergies involved. So that energy being injected in the transformation centers in our grid transforms to movement, but some of it becomes heat. We have substations and switchyards that are connected in parallel. We have reduced a lot the heat generation and the energy loss related to the braking of trains, the rheostatic braking of trains. So right now we are in very good operating conditions. We have reached a 95% of energy recovery when we have a lot of trains in the line and when there is a synchronous operation of those trains. Let's not forget that apart from these processes of degradation and loss of energy by the movement of trains, we will also have a direct heat um, exchange due to the climate, due to the conditioning of the environment inside the trains. We have around 15 kilowatts for wagon, which could be a lot for the whole train. In order to calculate how much energy is consumed by the trains and after that calculating the heat that they generate, there is a middle stage that is really beautiful for me, which is the um, simulation of trains. What we do with this, we transform the information about the geometry of lines, such as curves and straight lines. We transform all that, the dynamic characteristics and the geocinetic. You see the curves of traction and braking. In Madrid, we transform all that to cinematic parameters, and specifically mechanical parameters, the effort that that train needs in order to move, the speed needs to meet several criteria, such as being efficient for the transportation of users, and there is an energy consumption which is characteristic of every train from station to station. And this is a very deterministic parameter thanks to the automatic modes of circulation. This process repeats itself train after train in a very regular way. But it is not as easy as summarizing the totality of trains. If you add up the figures, the total energy consumption comes up. But there is also a nonlinear phenomenon that complicates it all, which is the wonder of regeneration. So there are some complications there for the calculation of the total consumption of energy because of that regeneration. We have powerful simulators that we ourselves developed, and the final outcome is a quantification of the energy being consumed in any of the substation or the switchyards that feed the line. A comparison of what would happen if there was no regeneration, and also specific parameters that allow us to design better lines when we, for example, need to construct extension of stations or lines. When we have in the pipeline different extension projects, well, these parameters will be extremely helpful. They will help the design. They will support different stages of the project, um, in not only for the electrification area, for the design of curves, for the design of the speed profiles, and also to guarantee the transportation capability. Apart from the trains, there are also important thermal loads, but first we need to evaluate the energy consumption associated to them. Is different facilities and installations that are there. We have lighting, we have elevators, we have switch yards that provide energy to small traction centers. And then you have different thermal loads, such as the lining, the vertical transportation, ventilation, air conditioning, and different services for the travelers. For those thermal loads, we have defined mathematical models. This is the one, for example, for the escalators in a station. That is the power that consumes an escalator in one station, which is influenced by some terms that will be deterministic, related to the structure, to the height, to the electric power, to the basic electric power when it is in operation without load, and also the weight of the users. But the weight of the users, we cannot identify that. So we need to calculate the number of users that will be there at a specific time. So you see that we need to see at different moments in time throughout the day, the light, the number of users, and other consumption sources that are more variable, that are more stochastic, such as the vertical transportation associated to the movement of users, and some other systems that will depend on the weather conditions outside, such as the air conditioning, also the water pumping, the water that is filtered in the tunnels that needs to be extracted to the outside, and we need to pump it to the collectors, and that depends on the amount of rainfall. So there is a stochastic process in order to model this variability, and we had to perform a very precise analysis. We were calculating all the milestones, and that allows us to calculate and to assess the evolution in time of the consumption of every single variable and parameter that will influence the electric consumption. So here, for example, you see how an escalation uh, is determined by the number of users using it. So we can aggregate all those consumptions at different levels. We could, for example, have an aggregation at a station level or at a network level, or we could integrate that in time, and we could have an aggregated result of the whole energy, of the total energy by one station or the whole line. Once we have that, we need to compare that to real results by the sensors that we have in our network in the traction centers. That's the way that could help us validate the approximated model. We could correct it with different techniques, metabolic and system identification techniques. So we have reduced the error through, for example, Karman's filters. This allowed us to end up the first stage of the modeling of the system. With that, we had a robust system that could allow us to generate knowledge about our network. Now we have the normalization standards coming from the ISO that have to do with energy efficiency. And this whole model allows us to know in detail what are the processes that lead to energy consumption so that we can project in the future um, improvement areas. So let's go back to the heat generation. So our approach is we have functions that relate the heat generated with the electrical consumption. We have those mobile thermal loads that are trains, and there will be a cascade of events, of situations that go like this. Technology has evolved in transportation systems, so this is not constant. But right now in the pole position, we have the air conditioning. After that, the braking of trains. The regeneration capabilities have made that the braking efforts are now in second position, especially when the air conditioning is uh, in operation. Well, they have a huge impact in the thermal conditions. We have all the heat generators related to the cinematic activity. So in summary, the most important factors are the air conditioning and the braking capability of trains. So now we have a potential estimation of what generated heat is and the electric consumption. You see all these factors included in this formula. If there is a sequence of trains projected in time and space, we have this formula. And through statistic techniques, we can associate that heat to a specific control variable. For example, speed, which is a parameter that is really controllable, and we have a direct reading of it. So if we relate the generation of heat in space and we relate that to speed, that gives us a lot of power at the time of managing the modeling system. There are other loads that will be included in this model. So you see, this is a mathematical model in order to evaluate the heat related to the air conditioning. There will be a spatial distribution that would need to be taken into account too. There are different techniques for that. Here you have the end of a simulation. This is the end point of an electric simulation, which is in the upper left corner, and the correspondence to the simulation of the exchange in a station, and we relate that to the braking of trains and also the environment of the tunnel and also the heat generated by the air conditioning. This process is repeated in different scenarios, different trains conditions, different speed conditions. So in the end, we have a collection of data, a collection of estimations of the heat generated by the trains and how it is distributed in space. For fixed installations, we can have a similar model. We can see the amount of heat generated by different parameters with that relation between the heated, without the, sorry, between the generated heat and the electrical consumption. So it is true that the train is a mass that generates heat and it moves. So the modeling should be easy, but but that is the kernel of the process, and it is not that easy because you need to know how heat is distributed in a station, taking into account the complexity of the architecture in different stations and the diversity of typology of stations because of the needs of transportation of the cities. Well, in this table, I try to represent in a scalable way a projection of the quantification of the heat generated by any of those factors for different scenarios, for different types of station. For example, a station of 5,000 square meters would have a distribution of temperature, which is homogeneous. You see the numbers, you see the figures there in different operation situations. So you see there is a regeneration which is acceptable, homogeneous figures. We can see the relative weight of those loads that will add up to have the total figures at the bottom that will be useful for our model. Here we have one of the main actors here, one of the um, main impactors, which is the ventilation. So we will not have a snapshot, we'll have a thing that moves in time, which is the ventilation. Ventilation systems have a huge impact. Right before, Professor talked about the high capacity of the ground to absorb heat in an enclosed environment. But when you open that environment and you activate the ventilation systems, the amount of heat that will travel with air increases quite notably. We have gone through a health crisis, so we have had to power up our ventilation systems in the underground network in order to have better health conditions, in order to avoid the transmission of the coronavirus through aerosols. We have increased the operation of the ventilation in the underground in a 150%. That could even generate some kind of inconveniences for the users. And now it is 100% active. So our system, which is a very standard one, we just put inside fresh air in the underground and we take out the air through the adjacent tunnels. There are different elements that help us do it in order to control the level of pressure, not only temperature, also pressure and other characteristics related, I mean, with the compensation shafts. So that is like a flute with many holes and it moves the air in many directions in in an anarchical way. And so an estimation is important in order to know how that air moves.
Nosotros disponemos de un sistema de
We have
ventilación.
a ventilation system which exists 900 fans and have ventilation management systems in 2017 which optimizes their performance. That system, which we call smart ventilation system, has allowed us to save 25% of energy consumption for the ventilation system and at the same time has contributed to redistributing thermal loads and the availability of energy, of thermal energy uh, to use for other things. Something else that I think is important is that tunnel ventilation is the one that moves the largest amount of flow. And we're talking about 250,000, 300,000 cubic meters per hour. In addition to forced ventilation, we have other means that we can use to generate ventilation naturally, such as the density gradient, the chimney effect, or induced ventilation, the piston effect, which moves air but in a lower amount. So the idea that we propose is quite modest, quite simple, but a little bit laborious to develop. Since we didn't think of any other way how to measure heat directly, but we can measure temperature directly, we established a thermal balance in different areas of our network. And in that thermal balance, which has an analytical solution that is kind of simple, what we did was to evaluate the temperature within different points inside the network by using some of the source terms that I use, heat transfer, heat balance, etc. We use also flow matrix to determine what was the movement of flow within the system. And that allowed us to obtain a number of parameters. That was some kind of like a dance between different components and different materials and parameters, one condition and the other. It's kind of like a dance. Sometimes the leading role would be by the heat. Other times the flow would be transferred to the different thermal sumps, such as the soil or the outer air, the external air. And that balance between the internal heat flow and the heat that is going to be transferred to the external air, it's going to be in constant contact, in constant exchange for a long period of time until we stop using trains. This is the mathematical model, kind of the flow diagram that is used to obtain the different equations that we use to develop our models for the different domains that comprise our subway network. On the one hand, we have the halls of the stations where things happen. The size of each one of those areas is going to be determined by the specific times that are part of this. For example, some of the phenomena of the things that happen on the way in and the way out from the subway station, which needs more time so that they can be assessed and represented accurately. And then in the tunnels, we have a number of things that are going to have to be considered so that we can accurately consider the external aspects that take part in the different connections with the outside world. You know, the sumps play a key role, for example, the soil, and also the external layer, which is connected to through the extraction system and the emission system inside the station, and also the compensation network in and out of the stations. In all of this, we consider a model which tested many of these parameters, parameters that kind of had to be put together, kind of like a puzzle, so that we could put together the global picture. We are able to know the evolution of thermal load based on the process that has been developed based on the power consumption. Then we infer what the heat generation is, and we make that dynamic based on the traffic of trains, and that is comprised of a number of pieces which I mentioned earlier. And also we have an evolution in time. This can be animated considering how ventilation works. In red, we see the operation of the fans for one of the tunnels. The tunnel on the right-hand side has a different performance. In this case, I think it's the same one as the one on the left. And then we have ventilation in the station and the two natural mechanisms of mechanism. The green one is the piston effect, and the induced ventilation, which is natural ventilation based on the thermal gradients. That is the purple line that provides us with the temperature evolution that we compare with the temperature probes that we have in different stations. And by testing the model and correcting things to make sure that our equations are accurate, consider models such as, for example, floatability, aspects that we're not able to model, what we do is to indirectly uh, model them in these equations to ensure that the final error is less than 5%. Once we've presented the model and we can provide you with a clearer idea, what we do is to quantify how much it was generated in the network by putting together all the different pieces with for different types of stations and different operational conditions. We build a kind of tensor, and then that gives us different performance conditions and a generation map that considers all the different scenarios that take place in our network. Here you have a typical summer day, a thermal map of our network of a summer day, in which we can see, you know, a station which is subdivided in a number of general criteria that has been considered by the mathematical model. And then, because of its importance, the model also considers the different types of ventilation systems that can be used throughout the different metro lines. For example, the police stations are stations which do not have uh, platform fans, whereas the stations where we don't have tunnel ventilation, the entire ventilation is depends on natural phenomena, are the ones that have a darker color. Then we have surface sections, and then the results in which we have a red dot or red color are stations where we have the larger amount of heat. We're talking about heat transfers of about 4 megawatts per day. This summer day, the same thing applies to the winter. We've done this for all, for every day throughout the year. But as I was saying, if we do it for a winter day, there are stations in which the heat transfer is much lower. This gives us an idea of where energy can, where it makes the most sense to have energy collecting devices in some stations. And I think the result is quite significant. I think having this information available is very useful. To conclude, I wanted to share with you a couple of examples. Since we said that we needed to strengthen ventilation, and in extraction wells is where we have the largest amount of flow, it's important to consider that if we're somehow able to make use of that enthalpic flow that comes out of the tunnels, well, that would be very good. For example, using a heat pump and then measuring what is the heat that is going to be available in the vaporizer, in the pump vaporizer, is also going to be very useful. That's going to allow us to size our thermal equipment properly, considering that we don't have much space for that equipment, which means we cannot use large heat exchangers in those areas. So if we're talking about a cold winter day with large thermal jumps of about 10 degrees at night time and even significant slopes within the terrain, especially now that we had to reinforce ventilation significantly because of the pandemic. Well, in such cases, we can have situations in which the use of energy in those extension boxes are quite significant. This would be the timeline of our thermal power availability throughout the day in the different hour windows by means of a heat exchanger that would be installed in the extraction box. This is something important to consider, because if you want to have all that energy available and you want to have hot water, this is the energy that's going to kind of power your heat pump. In this particular day, I wanted to say that the method allows you to quantify how much heat is injected into one of the grills. For example, in this situation, whenever the fans are working, we'll be injecting cold in the station. That cold that is injected in the station is going to condition the air temperature inside, and is going to help us to regulate the temperature delta between the outside and the inside. In let's say spring or fall day, the outside temperature is going to be higher than the temperature of the terrain, and that's where the dance, the interaction between the different parameters is going to become increasingly more important. Heat transferred to the heat to the soil is going to be more dominant, and our heat collection is going to be affected. Here we see that we're injecting heat when we put the fans into operation, and then this is magnified in the case of a summer day. The amount of energy that we're going to be able to use is going to be reduced. The number of energy that it's going to be able to use for a heat pump. Similarly, we can assess the amount of energy that is obtained from the terrain. Here we have a kind of situation in which we're extracting heat from the terrain and we're pumping it without any pump, just by natural means, added to the heat that is generated in our facility, and that's going to be pumped to the geothermal equipment. And even under those conditions, the heat pump is going to make a lot of sense and it can be used. In the summertime, we're going to have a situation in which the flow of energy to the terrain is going to increase significantly, and the heat pump is not going to be as relevant, but it's going to be much more important for the geothermally activated system. And then to conclude, the addition of the model that I just presented results in a rate ranging between 350 to 450 gigawatts hours in all stations, highly distributed, as you've seen, and highly focused on in some areas, especially in the central part of the city, probably because of the thermal characteristics of the soil there. The process is highly dominated by the level of regeneration and HVAC, both in trains and in the stations. And then we have a ratio that is quite interesting, which relates the thermal energy that is produced in relation to the thermal energy that is consumed, which ranges between 65 to 80%. In conditions of forced ventilation, one of the things that we're able to do is to maintain a temperature that's more or less stable in time, which means that the thermal gap is not significant between morning and day. So, thanks to that smart system, we are going to be able to have up to 60% more heat in some stations and in specific configurations. 60% more energy, as I was saying. And then in the summertime, we're going to have a significant capacity to use energy, especially in terms of the heat exchangers that are installed in different stages. Although there is the challenge that we're talking about exchange surfaces that are quite large, so it's very important to know very well where the systems need to be installed so we can make the most of them. Outside of that optimal capabilities, the heat generated is used to increasing the temperature in the stations. It's going to allow us to increase our control of temperature stability in the different facilities. And we know based on experience that once the temperature goes into those limit systems, because of the different cold spots and hot spots, then it's very difficult to kind of return them to the balance point. So that's what we want to be. That we want to be in the balance point so that we can control how much heat we're being able to exchange. Thank you very much for your attention.